Is it listening? It is listening. Yay. Okay, cool. Then we'll get a better quality video now. Where you're seeing exactly what it's doing. Okay, so then let me remind you the last thing we did. We saw these series that go to infinity, basically like add numbers forever and forever. And you're wondering, basically the question is, do they ever converge? And we saw geometric series do converge if the common ratio is less than one, or like the R value is what we called it. And then we had this test for like whether they converge or diverge. If the terms themselves aren't getting really, really tiny, if they're not going to zero, like this one didn't, then they for sure has no chance of converging. But that was a test for will it diverge, because if the terms do go to zero, then it doesn't tell you anything. It doesn't tell you whether for sure it will converge or not. It just has a chance of converging. So today we do tests that will tell you for sure whether it converges or diverges. But I think the first thing you did, like a good first filter before you start trying any fancier math like I'm about to teach you, is to do the nth term test first. Whether you write it down or you just do it in your brain, that's a good filter to see if it's even worth your time to check if it converges or not. So that's how I'm going to do these. I'm going to do the nth term test first, just so you get used to it, and then I'll do the integral test. But the integral test, it's pretty easy to summarize. Basically, it says if you have a sum that you're wondering if this converges or not, you can take the integral of that same function, like 1 over 3x plus 4, from here to here, so wherever it started to wherever it ended, or actually from anywhere to infinity. It doesn't matter, but it's just conventionally you put the wherever this started. So if this started at 1, then the integral should start at 1. So 1 to infinity, and if this integral converges, then the sum converges. And conversely, if the sum converges, then the integral converges. Kind of wild, but you can. I'll show you why that is later. And these three things are important to keep in mind. The integral test only applies if those three things are true. And I've seen the AP test ask that straight up, like, what are the three conditions for the integral test to be applied? So those are just good to know. It only applies if your function itself, 1 over 3x plus 4 in this case, is continuous, it's positive, and it's decreasing on this interval from 1 to infinity. Okay, so in this case, let me not even check them formally. Is it continuous? Well, there's an asymptote at negative 4/3, but that's not between 1 and infinity. So yes, it's continuous everywhere else. Is it positive? Yeah. I mean, this is positive on top, and between 1 and infinity, if I plug in numbers from into the bottom, I only get positive numbers. So yeah, it's continuous. Yeah, it's positive. And yeah, as I plug in bigger and bigger numbers, this will become smaller and smaller. Cool. So yes, continuous, positive, increasing, done. Then, is it even worth wasting my time doing the integral test on this, or will I know for sure that it won't converge using the nth term test? Let's check. So like I said, this is just a good habit to get into, whether you do this in your brain, like just looking at it, or you write it down, do the nth term test first. So here's us doing that. Nth term test. That's the one that says, take the limit as n goes to infinity of the terms themselves. If that doesn't go to 0, then you know for sure it's divergent. But in this case, hopefully you see you get 1 on top is constant. The bottom gets bigger and bigger and bigger and bigger and bigger. The 1 over a huge number will go to 0. Cool. But remember, this tells us not that it converges, but that it has a chance of converging, possibly. Could possibly converge. Nice. Okay, so how do we tell if it converges or not? We do the integral test, or at least this is our only tools this far in the unit. Cool. Okay, so then let's do the integral test. That means take this integral 1 to infinity. And then this is just also a good review on improper integral. Okay. So hopefully, do you guys remember improper integrals? If you don't, they're just basically an integral where you take the antiderivative of this, you plug in infinity and plug in 1. But infinity isn't an actual number, so you're not allowed to write I'm plugging in actually, like you can't write 3 times infinity plus 4. Instead, you take the, what do you remember?
That's like a letter.
Yeah, precisely. Yeah. You say, let me go not from 1 to infinity, but from 1 to this number, b, and see what happens as b goes to infinity. 1 over 3x plus 4. And like I said, in your brain, you're not thinking any differently. You're thinking, take the antiderivative, plug in infinity, plug in 1. But this is the way you write it formally. All right. All right. So antiderivative of this fraction, you guys know it off the top of your heads, or should we do it along the way? Good job with the 1/3. Yeah, good job. Yeah. If you didn't see that, then you would have to do a whole u substitution. Where u equals 3x plus 4, therefore du equals 3 dx, and therefore when you solve for dx, you get that 1/3 that these guys are talking about. 1/3 du equals dx, and so therefore you have this extra 1/3 in front of your whole fraction. But since you guys saw it, let me skip the u substitution. Make my life easier, just jumping straight to the antiderivative. Natural log of 3x plus 4, except the extra 1/3 is 1, so divided by 3 or times 1/3. And then I'm plugging in b into 1. Nice. All right, notice that this one, there's a whole function down here, but I still said that the answer is natural log. That's because this function is linear. If it had been 3x squared plus 4, then it's no longer natural log of 3x squared plus 4. Did I make that clear yesterday? Okay. Nice. All right, cool. So then we plug in b, we plug in 1, and we see what happens. Plug in b, and I get 1/3 natural log of 3 times b plus 4 minus 1/3 natural log of 3 times 1 plus 4, which I'm just going to write as 7. There it is. And then I take this limit. So what happens as b goes to infinity in this function? Do you guys have any idea? Yeah, okay. Okay, all right, good. Yeah, nice. You guys, good job. Yeah. This looks like a scary thing, but again, if you know your parent functions, then it's not that scary of a thing. For sure, the 3b plus 4 just gets bigger and bigger. So you're taking the natural log of something bigger and bigger and bigger and bigger. So basically, you're checking what happens to natural log as you go forever to the right. And natural log grows very, very slowly, but it does grow up to infinity. So this goes to infinity. Minus this doesn't change. And so you get a final limit of infinity. Very cool. And then let me make sure I explain this okay. It says determine whether the following series converge or diverge. I did this integral. I got that red answer. So what's that mean about this? Oh, it's that. Yeah. Okay, very. So then therefore, this series n equals 1 to infinity 1 over 3 again plus 4 is divergent. Nice, y'all. Okay, but I thought you said that one that was greater than 100. like an infinite number. Wait, hang on, you're mixing a lot of things together. And then saying the result. But no. First of all, I said up here the difference between what we just did and the things we were doing yesterday is yesterday we got a bunch of these guys, which were geometrics that are very, very specific type of thing. So these we know will converge, but not when R is greater than 1, when R is less than 1. So when this is 1/2. So those were the two things that you mix together.
Yeah.
But yeah, it has to be very, very specific type of function or sum that we know will for sure converge. That's geometric. Right now is the only one we know converge. Oh, and actually watch this. Well, maybe this isn't. Okay, but what I was going to say is Eden, remember yesterday I told Eden there's certain types of functions that go to 0, or like certain types of series whose terms go to 0, but they still don't converge. Like this is the example I gave, 1/n, and the one we just did is very, very similar. I mean, it's 1/3n basically, and so it should make sense. That if the one I gave you yesterday didn't converge, then this one grows at a similar rate, so it's also not going to converge. Nice, yeah. Nth term test. Yeah, okay, in this particular example, it is a little bit silly, but I'm trying to get you guys used to just doing that in your heads before you even try any math. Even though, okay, you're right that I could have skipped the nth term test and just done the integral test, and that tells me convergent or divergent anyway. But in the wild, if you ever see like 4 sums and they ask you which one converges, the first thing you could always try is the nth term test and get rid of some of your options. I think that that's a good first filter, like what I was saying before. So I'm just trying to get you used to the nth term test. Do you have to write it every time you see a sum? No, you could do it in your brain, but I was trying to do it for you. Other cues? Nice, y'all. Okay. Next one is that one. My spacing is weird because I messed with the document yesterday. So let me give myself more space. Okay. Okay, so same idea. Nth term test was a good first filter, but can you see that these, well, if I could take the limit of this as n goes to infinity, what will that be? Here. Yeah, okay, so chance of converging, but we'll see if it actually does. Let me not write the nth term test this time. Let me just take the integral from 1 to infinity, 1/x cubed dx. Okay, nice, very cool. And oh yeah, correct. Then as b goes to infinity, it can go from 1 to b, 1/x cubed dx. Okay, and then do you guys remember the antiderivative of this, or a way to get the antiderivative? Remember? Yeah, exactly. Good job. Yeah, don't just say natural log of x cubed. Again, that's not a linear function, so you can't do that anymore. You gotta, or at least I have to, like keeping it written like this makes me think harder than I want to think. I just always rewrite that as x to the -3rd, add 1 and divide by the new power, and I get this. Dang. Okay. I get x to the -2nd over -2 at b and at 1. Okay, and then let me do a lot of things at once. First, let me rewrite this as a fraction because I think that'll be easier to take the limit of. So let me write this as Well, there was a -2. So -1/2 squared. I guess I just did one thing at once. And then I'll plug in b and 1. Yes? Oh, nice. Plug in because this question just asks, does it convert or type? Well, I can't decide. I think it's better to plug the numbers in. What if you yeah, what if you miss something without plugging in? So like for example, what did yeah, okay, I think you guys are ahead of me. Good job. Limit as b goes to infinity. In this case, is very, very easy because then the bottom is getting huge, like Eden said. So this will go to 0, but then your final answer will be +1/2. Okay. And then the reason I'm saying plug, like in this case, it's good to actually plug in the number is because down here they ask us something about that integral. Like on the next question, they ask us something about that integral. So it's good to know that this was 1/2. What? Oh yeah, correct. Yeah, this asks us, does this convert, divert, does this convert? All right. Question on that? Let's say that again.
Why did you put 1/2 or something?
Oh, 1/2 is the final answer for the integral. But it does not converge exactly to this, but it does. This does give us a hint of what it might. It converges somewhere close to 1/2. And actually, unless you were talking about that's what the integral converges to. The integral converges to this. The sum does not. But it gives us a hint of what it converges to, which is what the next little section is about. For me, that's on like kind of the next page. But it says, look at if you want to know what this sum converges to, like what the actual sum value is, then you can use these bounds. It says the sum will be somewhere between the integral value and the like first term plus the integral value. And let us do an example first, and then we'll talk about where this comes from. Because it's I think it's a really, really neat little thing. That tells you a nice little bound for what your sum should be. Okay, that's all we need right now. Let's get the bounds, and then I'll talk to you about this bound, this error bound, and what that means in a second. Sorry, mine looks different than yours. I had to mess with the formatting. But it says find an upper and lower bound for this series, which is the series we just took. So this sum will be between these two numbers. First of all, it'll be between this integral and the first term plus that integral. Yeah. So first term meaning plug in whatever k is equal to down here at the bottom of the sum. The first term in this case would be 1/1u, which is 1. Question?
Is the not like the C value, the integral?
No, that's a good question. It does kind of look like that type of thing where I say like C of 2 plus 2 to 5 or whatever. No, it's a different thing. I'll show you what this is from in a second. Or actually, you guys might be able to think about it yourself.
Looks like the
It does look like the average. It does look like one of those functions where you you take the antiderivative of C prime and you get C of 5 or whatever. But it's its own thing. It might be related to that, but I just don't see the immediate connection off the top of my head. But anyway, let's finish this. We got that this integral was 1/2, was it, on the last page? Okay, so then this is between 1/2 and 1 plus 1/2. Which is a good enough answer. But if you wanted it to look really nice, you could say 1/2 and oh wait, what the heck? This is written kind of in a funny way, but 1 plus 1/2 is 3/2, is all I was going to say. But then I noticed that this says K and this says N, and that's wrong. That's not right. These letters should match. So either make this an N or make this a K. I guess I'll make this a K. Just so that the letters match.
Do you also want the X's match the N
No,
or
no, for the integral you want x's in there, kind of implying that this is one continuous function, not discrete, like whole number value function. All right, now here's the first interesting, well, okay, the whole thing is kind of interesting, but I think the really interesting bit is where these guys come from. I don't know if it's too early for you guys to think about it, but here is a big hint. Here is the graph of 1 over x cubed. The integral from 1 to infinity would look something like this area here. Okay, all right, okay. Nice. What about if you were to draw this sum, represent this sum as some sort of graph? You guys have any idea?
higher?
What do you mean?
Like everything underneath that graph, like all of that add up.
Except this graph includes things like this one is just 1 over 1 cubed, 1 plus 1 over 2 cubed plus 1 over 3 cubed. This one includes 1 over 1.2 cubed. Like this function. You just want whole number discrete value. Do you have any idea what I'm getting at? Hey, wow, great job. Yes, exactly. Nice. Yes, really good. That was really quick. Yeah, that's exactly where these bounds come from. Watch this. If I make a left Riemann sum of this dude right here, let me do it at 1, at 2, at 3, at 4, at 5, and in a different color, maybe red. Then watch this. Here's a left Riemann sum. Hey, more like, well, we'll talk about it, but yeah, this is one of the bounds. But watch this. F of 1 would be 1 over 1 cubed. That's the first term of this. In other words, this little dude has area of first term, a sub 1. Let me call it a sub 1. This red box has area a sub 2 for the same reason, like second term, 1 over 2 cubed. This dude, a sub 3, a sub 4, and if you were to keep going, then these little boxes, the area of those boxes, since it's f of 1 times a width of 1, this is just the sum, exactly. Like the area of these boxes represents the sum, yeah? And you see how the red boxes are obviously above the actual integral? So that's where this bound comes from. Let's scroll up. Sum is bigger than integral. Whoa, awesome, cool, nice. All right, but then what about the other one, the one that says sum is less than first term plus integral? This one is not as obvious, but it has to do with the same idea. If you come up with it, I would be very.
Like the reverse of it.
What do you mean the reverse of it?
Or I like taking the other side.
Yes, exactly. Hey, good job. Yeah. Yeah, if you take this and interpret it to be a right Riemann sum, then let me see if this is not too much color on one page. But if you take this to be the right Riemann sum, now that also has an area of f of 1, or a of 1, a sub 1. So there's your first term, a sub 1, and then plus the integral over here, that would give you an area less. Let me draw the rest of these green boxes. All these green boxes are under the actual area. And so the first term plus the rest of these boxes, that's the sum, and that's under the value of the first term plus the black area. Can I explain that good? So, okay, I think in a month when you like a month and a half when you take this test, you're not going to remember these bounds, but you might remember that it has something to do with the Riemann sums and be able to get the bounds and stuff. Plus, I just think that's a cool little idea. Like it's so simple, but it gives you good bounds. Good stuff. Yes.
So like, is all of that you just said it's something that like help us?
It's to help you conceptualize it.
Oh.
If you're good at memorizing things and you'll remember this, then that's fine. You can just memorize that.
That's just like where.
What if it was just like a function of x cubed or that would be increasing so that the left Riemann sum to like under x and the right zero.
Nice, except watch this. I don't got to worry about that because the question was for the video, what if the function was increasing? But I don't got to worry about that because it says it's decreasing. Nice, Kian. You guys, good job. Good question. All right, 8:31. Okay, this is perfect timing, unless there's more questions. All right, cool. So now you know if you see a sum and it's not geometric and it doesn't fail the nth term test, as in the limit does go to 0, then you can always do the integral test and see if it converges or diverges. Also, I forgot there's one more about the integral test. And then I got another little section for you guys. So let's do this one real quick. That one says, approximate the sum of the convergent series this by using 6 terms, and then include an estimate for the max error of your approximation. So what this means, actually, if I wasn't here, would you know what this means? I'm talking about this using 6 terms thing. You know what that means? Yeah, exactly. Okay, yeah. Use the partial sum. Don't add this all the way to infinity. Add 6 terms of this sum and use that as an estimate for what this entire sum would be. So, okay, let's do that first. Approximate the sum using 6 terms. Okay, I will. This partial sum, n equals 1 to not infinity, but now 6 of 1 over n to the 4th would be, here's me plugging in the first 6 terms. First term they told me was plug in 1. Okay, I will. 1 over 1 plus 1 over plug in 2. And I get 2 to the 4th is 16. Plus 3 to the 4th. You guys know that one? Nice. Plus 4 to the 4th. You know that one? Yeah, no one knows that.
256.
Whoa! 256 plus 5 to the 4th. Nice, it is. It's kind of interesting. And then 1 over 6 to the 4th, for sure nobody knows. Or if you do, I'd be very impressed. Yeah, okay. This one's 1296. Okay, so there is my 6th partial sum, as in I plugged in 6 terms, and I'm saying this is a good estimate for the entire sum. This ends up being 1.0811. I don't know what that is. It's a fraction. Desmos didn't give it to me as a fraction. Cool. Nice. And then it says, of course, adding from 1 to 6 is much different than adding from 1 to infinity. So how far off is this value from the actual sum value of 1 to infinity? So that's what it says. Approximate the estimate of the maximum error. This would be hard for you to just come up with yourself. But in this box, I told you, here's the bounds. It'll be between lower bound and upper bound. But then there's this other part to the box, which looks better on your paper, that says the maximum error for any approximation up to n terms, like up to 6 terms in this case, is given by this Meaning, short version is that it's the integral from 6 to infinity of the function. Okay. And it has to do with the exact same thing that we were talking about over here. Like, in fact, this green thing, if you cover up the A1, tells you why, like, the maximum error would just be the integral for the from 1 to infinity. Like, use this exact picture and you can convince yourself of this value. But I'm trying to get through 2 more things in 10 minutes. So let me just say maximum error is equal to the integral from 6 to infinity of this function. If we had a lot of time, we would take this integral, but it's exactly like the ones we just did, where we take the antiderivative, we plug in infinity, we plug in 1 or 6 in this case, and subtract them. So let me skip that part and show you that this integral is equal to 1 over 648. And then just for fun, do you guys know what this means? 1 over 648. But what does it mean in terms of like our error? Like, what does it mean maximum error? Yeah.
area.
Nice. Yeah, exactly. Our sum, we went up to 6 places and we got 1.0811. That's not exactly right, of course, because we didn't go all the way to infinity, but it'll be within 1/648 of the actual answer. So the answer will be less than 1 over 648, less than 0.0015 away from the real answer, which is kind of neat. We just went 6 places. If we had gone infinite number of places, we would have been off by 0.0015 at most. Kind of interesting. Ian and then Eden.
Just because it's like we can tell that it's only positive with n to the 4th, we don't say that like it has to be above that rather than like the maximum error can only get above that.
Nice job. Yeah. So it's not 148 in each direction. Like it might be 148 less or 148 more. But Ian's saying this is always positive. You're always adding more and more and more. So this is this approximation that we got is less than the actual amount by at most 1/648. Nice. Yes. All right, Eden and then Jeremy.
For the equation up there for the maximum error equation, it says k equals n plus 1 though, so why would
That's saying, okay, yeah, yes, good job bringing that up. That's saying I got the sum from 1 to 6. If you wanted to know how much the rest of the sum is equal to, so from n equals 7 to infinity. Oh shoot. Yeah, it is. I got the sum from 1 to 6. The rest of the sum from 7 to infinity is going to be less than or equal to the integral from 6 to infinity. So we're good with what we did. But yeah, good catch.
that basically
Say that again?
both of them? The maximum,
Yeah, I mean, these are talking about the same thing.
okay.
These are just different ways to write it. Okay, is good with that. And then I got one more like little section that's pretty easy in 7 minutes. Okay, last little bit of this section is called P series. Let me make that look nicer. There. All right, P series. So we talked yesterday about geometric series. Geometric series are the ones that look like usually they start at 0, go to infinity, and they look like that. PC, and I told you these are a good baseline to see, compare it to other sums that you see out in the wild. If it looks like a geometric one, but it grows slower, then probably converges. If it grows faster, it probably diverges, etc. Like this is a good baseline. Here's another new baseline that you're getting is P series. P series are the ones that look like this. I'll just point at it, where it's 1 over n to the p. And when I was first learning this, up until like pretty recently, I would always get these confused. But Geometric series are the ones where n is the what's it called, the exponent, and p series are the ones where it's like 1 over n to a constant power. So you'll see examples on the bottom. But the summary of this is that it's kind of what you would expect. If p is a big power, then this is like shrinking very fast, you know, because it's like 1 over n to the 5th is going to get big on the bottom fast. And so if p is bigger than 1, if the power here is bigger than 1, then this will converge. If it's between 0 and 1, like 1/3 or 1/2 or whatever, then this isn't getting this is getting big very, very slowly, meaning this isn't shrinking, that the whole fraction isn't shrinking fast enough for it to converge. So these diverge. And then big one, important one, the one that I was telling Eden about yesterday. This, if p is exactly 1, then it looks like this: 1 plus 1/2 plus 1/3 plus blah 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 plus 1 over n. That one feels in your heart like it should converge, but it doesn't. It diverges, and if we have time at the end, that's a neat proof as well, or a neat little idea of the proof of why that diverges, even though it feels like it should converge. Okay, so like here's 2 examples. Watch this. This is a p series, even though it doesn't look like 1 over n to the power. You can make it look like 1 over n to the power. You guys see what I'm talking about? 1 over n to what power? 1 over, okay, 1/3. Therefore, p is 1/3. So does this converge or diverge? Diverge. Diverge because p isn't big enough. P equals 1/3. That's not bigger than 1. And then does this one converge or diverge? The one on the bottom? Yeah, that one converges to pi fourths is bigger than 1. That's it. Hopefully, yeah. But what they do sometimes is they'll say like, which one of these 3 theories converges, and they'll say this one, and this one, only this one, or only a third, or something like that. And so you have to know how to compare and contrast and pull out p series from geometric series from other series. Yeah, it's kind of intense. It converges to p is 5/4. I'm gonna guess where I have to write that without it. Oh, if I write it down here. That's as good as I can do. All right. There you go. Okay, and then why does it diverge? Why does the harmonic series diverge? Again, I think that's a neat little thing, so let me see if I can get through it in 3 minutes. If you have to go, like, feel free to go. One speak. All right, watch this one. Okay, there. I wanted to get to 16, I think. All right, here's a good intuition as to why this feels like it should converge because the terms are getting small, but it actually diverges. So watch, it's not that you have to write this, but just like I get asked this all the time, like why does this diverge? It feels like it shouldn't. Watch this. So first term is obviously 1. Second 2 terms let me do it like this. 1 plus 1/2. I've changed nothing. Okay. Third term, please agree with me that 1/3 is bigger than 1/4. 0.33, 0.25. Okay, so this sum up here this sum, I don't know how to write that. This sum in black is bigger than, do this. Black, bigger than red. All right, watch this. This you agreed is bigger than 1/4. So let me change this to 1/4 plus 1/4, not change to 1/4. Then please agree with me that 1/5, 1/6, 1/7, and 1/8 are all bigger than 1/8. All right, so then this would be, oh. Okay, black sum's still bigger than these because I changed a 5 to an 8, a 6 to an 8, a 7 to an 8, and an 8 to an 8. So black is bigger. But you can see what I'm doing now. Also agree with me that 9, 10, 11, and 12 are all bigger than the 1/16. Yeah, I need 8/16s here, which I don't know if I'm gonna do. But the idea is that now these are adding 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2, which is of course gonna die. Yeah, it's getting bigger, bigger, bigger.